thing that you drew, instead of drawing a resistor, you had drawn a capacitor, would that not have, I mean, would there just be no resistance, and then therefore the EMF would be equal to 0, because the resistance is equal to 0? Maybe I'm thinking
No, what would happen is, let's see. There would be an EMF. So if there's no capacitor, if it's just the ideal wire,
right.
then you would find that the current would be huge, or if not infinite. And what would happen? Oh, as the current increases, remember that force was opposite direction of movement? So if that current becomes huge, then that force is going to become huge also, and gets harder and harder to move it off to the left or to the right. And you actually can see this. If I've got a superconducting surface down here, and at this point, you can create that. I've seen tracks that you keep them bathed in liquid nitrogen to keep them cold enough for superconductivity to be working. Superconductivity, no resistance. No measurable resistance. You then take a magnet, and the ones I've seen, we actually have one around here somewhere. Just a small little cube of a magnet. If this is superconducting, so no resistance, I can take this magnet and I can just drop it. Now what happens as this has a north side and a south side, so let's just assume that's north and this is south, so I've got north and south, so north and south. As it falls, I'm going to get a change in the magnetic flux in the surface here. You can see the actually drawn into it. Because I have a change in magnetic flux, I'm going to induce a current here, which is going to oppose. My magnetic flux is increasing, so it's going to try to oppose that. It will create a current which is basically fighting this. It will create so the induced current will create basically another magnet down here with a north and south pole like that. So this magnet is going to be repelled by the surface. The magnet is then going to stop. When it stops, let's do a chicken and egg argument here. See if I can avoid that. Magnet starts to fall, it induces a current which pushes against it. That current going against it is going to basically stop it and bounce it up just slightly. When it stops though, the current drops, that magnetic field will also drop. There's a time lag in there somewhere. And so then it'll start to fall again, but as it starts to fall, it basically creates a current which opposes that. And so what you end up seeing is that this will hover. This is known as the Meissner effect. I think 1S. So in the case of, if the resistor were not there, then current would hit infinite very quickly and you wouldn't be able to move it, so that bar would stop. If you threw a capacitor in there, you would get a charge build up on the two plates, but then when it stopped, you no longer are forcing charge onto it, so the charges would then repel each other and then go back to where they were before.
Didn't realize it was as complex a question as it was. I was like, well, we did 40 divided by 6, so 6 is 0. That's where my head was at.
Yeah,
I appreciate this, but I am still, I think it's okay.
If I figure it out, I'll throw it in on the desk.
Great.
All right. That'd be a great insight. Oh, okay, great. They should have figured it out by now.
Right.
Let me see if I can. I'll I'm feeling good with the, if there's no component, it's just ideal wire, what's gonna happen, but.
Wait, you're still working on that problem? Oh,
I was just writing a note.
okay, got it.
All right, so now, I have a power supply here, of course, with a switch, solenoid. I flip the switch down, circuit's complete. Which way will the current flow from the power supply?
Isn't it two?
I assume you were doing clockwise.
Clockwise.
Yeah, okay.
Go
All right, so the current from the power supply is now gonna flow this way, so I've got a current flowing that way, current flowing this way. So in blue, I've got this current from the power supply. My solenoid, I suddenly have a current flowing through it, so remember the magnetic field inside the solenoid, in the middle of the solenoid, was equal to mu sub naught n sub I, or not n sub I, n times I. So that's the permeability of free space times the coil density times the number of coils per unit length times the current that's flowing. That magnetic field is going to, well, if I goes from 0 to something, then that means my magnetic field goes from 0 to something. If I think about the coils, I got a magnetic field that's suddenly building up in here, so what does that tell you about the magnetic flux of the solenoid?
It's building up as well.
Yep. And if I have a magnetic flux that's increasing, what's gonna happen?
Secondary induced current to oppose it.
Yep. So I'm gonna have a second current trying to oppose the change, which is called I sub 2. That's flowing the opposite way. Under normal circumstances, what that's gonna do is slow down the rate at which the current builds up. So if, without that in there, if I just have a perfect wire there and I throw the switch on, well, it's gonna quickly go to infinity if I have no resistance and perfect wires. If I throw an inductor in there, it's not gonna go up as quickly.
By inductor, are you referring to the solenoid?
Oh, yes, I guess I used the term a little bit too soon. That the fourth component's an inductor, that's. So let's. Kirchhoff's rules, I start here, I work my way around. So my change in the potential of the power supply plus the change in potential of the solenoid gotta be equal to 0. So if a change in potential of the power supply is positive, then this has gotta be a negative number. I have a change in potential of the solenoid because I have a changing magnetic field. So that's just gonna be, so delta VPS plus, yeah, I'll keep the plus there, plus negative change in the electric magnetic flux over change in time. Now I'm gonna make one alteration to this. The formula we talked about there, let's say that I have a magnetic flux that is if my magnetic field is changing at 2 Tesla per second. If 2 Tesla per second. And then I ask you, what is the changing magnetic flux through this solenoid? What would the answer be?
-2.
No. And I'm not worrying about plus or minus right now. Why is it not 2?
Because the graph we drew showed it was still going up?
No, not the reason.
Yeah, because that would just cancel it out completely, right?
Right.
Yeah, if there's no resistance, probably close enough, yeah. I'm not worrying about the fact that there's really of the ideal versus we have actual resistance here. All right, so what is magnetic flux again?
Magnetic field times the area.
Okay, area of what?
I haven't figured that out yet. The relevant thing that we're talking about in the problem.
What would the area be here? I'm not looking for a number, just description.
Would it be the surface area of one of the ends? Like
What is it, cylinder?
the area of the end of the cylinder?
You said surface area, I'm trying to think, surface area of what?
Like if you were to take the radius of the solenoid
Okay,
and calculate pi r squared.
so the area of the loop.
Yeah,
Okay,
sure. I guess.
all right, that's the A if I've got a loop there and I've got the magnetic field going through it. And so, then what's wrong with that? If I got a magnetic field that's going through here,
Oh, wait. So if, you're gonna have to divide this 2 Tesla by that area to be able to get,
ooh, gotta reword this.
right.
If the change in the magnetic field is 2 Tesla per second, 2 Tesla per second was the intent, that can't be changing magnetic flux, that's gotta be changing magnetic field.
Right.
So if my change in magnetic field is 2 Tesla per second, we'll make it positive. Let's say that the area here is 0.03 square meters. Why is my change in magnetic flux, the area is not changing on this? Why is the change in my magnetic flux not 2 times 0.03?
Because we have this induced current that has a magnetic field shooting off in a different direction?
No. We've sort of touched on this when we talked about a single loop versus solenoid. All right, so I've got this area right here of what I'm going to claim is 0.03 meters, square meters. How many loops are there? If I've got a magnetic field that's changing in the middle of every single one of these loops, my change in magnetic flux is not the change in magnetic field times the area of one loop. Every loop is having a change in magnetic flux. How many loops are having this? Now, you could look at it as, it is the change in magnetic flux, and the magnetic flux deals with in loops. So sometimes you will see, I will write it as say one loop. Textbooks tend to treat it more as, it's assumed this is for one loop, and you just multiply times the number of loops. So when we were looking at the change in the magnetic flux, how ultimately leading to that secondary current, ultimately we're going to get much more effective or use per meter by having a bunch of coils there, because a bunch of coils means I'm gonna have a lot more change in magnetic flux for the same current. Because everything in there is gonna be experiencing the same. And so, looking at this right here, we have negative N, change in B dot A over change in time. I am working under the assumption that it is not going to shrink or expand. So my area is going to stay the same. The magnetic field that's going through here, we got a formula for it right over there. So this is the change in mu naught little n I over delta t. We can pull out the constants. Oops, I lost some stuff there, minus NA. So negative NA mu naught little n times change in current over change in time. We're almost there. This right here, big N is the number of coils. A is the area here. Mu sub naught's a constant dealing with the material that's inside here, air, right now. Little n is the coil density, number of coils per unit length. This little n here, if you flash back, is just the number of coils per unit length. When you use the lowercase l, do not use an uppercase L in your notes there, for a reason that will become clear in just a moment. So this bit up here, we got this negative n squared A mu sub naught over L times the change in I over the change in time. This is the inductance. And the reason why I don't want to use a lowercase l there, or why I want to use a lowercase l there, is that the symbol for inductance is a capital L. And so we have a formula now for a resistor. It's just current times resistance. For a capacitor, it is Q over C. For an inductor, whether it ends up being positive or negative, depends on which way you go through it. It's L, change in I, or change in time. I am going to still stick the negative sign in there, but again, positive, negative depends on which way you're going. This relationship here, these three things here are also going to become very handy when we get to talking about AC current, which is coming up soon. Not today.
Did you put negative because it's opposite of the direction of the current? Like if the current's going this way, we call that direction positive.
Yeah.
Then it would be.
So technically that would be a negative there. And because that deals with the change in current, this deals with the actual current, direction the current's going, and by that token, I guess we have a change, no, not even change in current, our charts there.
We shouldn't
Depends
think
which
of
way
V
you're going
equals
around the circuit.
IR as V equals negative IR though, right?
Pardon?
We shouldn't think of V equals IR or delta V equals IR as delta V equals negative IR.
That's why I usually see the negative sign there, and I don't usually see the negative sign here. I know if I'm going with the current, I'm losing potential as I go across the resistor. Again, think through the direction, then work out the map. And Oh, that's right, that was not the warning, that was a test. So, ultimately, any of the components that we stick into a circuit is there to try to control current. If I don't want current building up too fast, I can throw an inductor in there. That's gonna slow it down. It won't stop the current, but it'll slow it down the rate at which it builds up. Capacitor, generally I want a capacitor in there if I need to store charge. Resistor, if I just wanna slow it down all across the board. Torn between two things. I at least want to get this other thing out of the way. So we'll come back to inductance. We've talked about Kirchhoff's junction rule, which basically works at any point in a circuit, whatever current flows in, flows out. And now the exception that we ignored. And not really an exception. I throw the circuit, charge starts building up on here. I get negative charges building up over here, positive charges flowing over here. I have a current flowing this way, and then the current flows that way. So I have this current, and that current are the same. So if I think about this as a junction right here, I have current flowing in is equal to, what? Current flows out over there, but what about at this point? If I have current flowing in, Kirchhoff says I should have current flowing out. So if Kirchhoff completely wrong. It's on how you want to define current. I know that there's an electric field between these two plates. And which way will that electric field go?
Point towards the negative side.
Okay, so I have an electric field going this way. And what is that electric field equal to? The magnitude of that electric field?